Today we are going to look at the inspection paradox. This is another type of statistical bias that can be quite subtle to detect, but can be used to manipulate the way people think about data. So let's get right down to business, and I promise you will never see bus stops, train stations, or crowded beaches the same way ever again. Once you learn to detect this pattern, I promise you, you will not stop seeing it. So get ready for the second episode of StatCat, where we use statistics to catalyze our decision-making processes and learn how to avoid falling victim to biases which might not reflect the information you think. The best way to understand the inspection paradox is through the waiting time paradox. We have all experienced this in one way or another when we feel that our bus or subway is never on time, or when it takes us forever to speak to customer service agents on the phone because our internet is not working. It is not your imagination. Throughout your life, you will probably experience longer than average waiting times for your metro ride. I'm an optimist, so rather than calling this bad luck, I will simply say that it is the absence of good luck, which I will explain later. Imagine it is morning rush hour and you're busy trying to get to work. As an example, let's say that there is a bus scheduled every 6 minutes. Now, if the buses were extremely punctual, then you could arrive at the bus stop at a random time, and on average, wait 3 minutes. The worst that could happen is that you arrive right as the bus is leaving and have to wait 5 minutes and 59 seconds. And the best would be to arrive simultaneously with the bus and wait nothing. However, life is never so simple, and due to traffic, your bus might be later than expected, or with some good luck, even earlier. Now, here comes the subtle bit. If a bus passes on average every 6 minutes, does that mean that on average we can still expect to wait 3 minutes? Well, no. In fact, as long as the buses are not perfectly synchronized, the average waiting time of passengers is going to be higher than 3 minutes. To see why, let's break down the first statement a little bit more. When someone says that on average a bus passes by every 6 minutes, it is equivalent to saying if you were to stand at the bus stop for 1 hour, you would see 10 buses pass. This is mathematically the same average, but now it is clear that there is no promise about how regularly they are spaced out. And to understand why the average waiting time goes up, let's consider some concrete examples. Imagine first an empty bus stop, and passengers are arriving at random times. For illustration purposes, let's say that one passenger arrives every minute. So we have our bus stop, and the first passenger arrives and starts to wait. This is followed by the second, the third, the fourth, and the fifth, until eventually the bus arrives on time and takes them all. Let's compare this typical scenario to one where the bus is late. As before, the passengers start to arrive at the bus stop one by one. They start waiting as normal, but then they realize the bus should have already been there by now and is running late. The number of people at the bus stop is just growing and growing. Eventually, the bus decides to show up and take the passengers. Finally, the bus station is empty again, and only one passenger shows up to wait before the final bus of this example arrives on time and takes her. This is just an example, so the exact numbers are meaningless. But on the first bus, the average waiting time of the passengers is 3 minutes, just as we would have naively expected. On the second bus, the average waiting time is much higher. In fact, it is twice as long with 6.5 minutes. The first unlucky passenger having to wait a full 12 minutes. And of course, on the final bus, the average waiting time was just 1 minute. Consider what a typical commuter would answer if you asked them, how much did you wait for the bus? If we asked a random person, we are more likely to ask a person that was on the delayed bus what is their experience, simply because more people were on that bus. In our example, more than 60% of the passengers experienced a delay longer than 4 minutes, with the average user experiencing a delay of 4.5 minutes. So going back to the earlier philosophical conundrum of absence of good luck. If the vast majority of people are experiencing something, then it can no longer be called luck, but rather that is the norm and a part of life to be expected. The reality is that the waiting time is on average 50% longer than the originally thought 3 minutes. So it is not bad luck to wait more than 4 or 5 minutes. It is perfectly expected. On the other hand, it is safe to say that the individual who only had to wait 1 minute and then had the bus to herself was indeed lucky. In other words, This bias arises frequently when we fail to consider the experience or perspective of the typical events, and instead we take a more convenient measurement approach. In our example, it is much more convenient to measure the number of buses that pass every hour and calculate the average time between buses than it is to ask random people how much they were waiting for the bus. Furthermore, there is a perverse incentive from the bus operator to report the former number, since it will always be a smaller quantity and make them look better. Once you learn about the inspection bias, you will start to see it everywhere. For example, when a university reports the number of students in an average class, the average is taken over all of the classes offered by the university. However, if you were to ask attending students how many peers they have in their classes, on average, you will find this number to be significantly higher. That is because when asking random students, it is much more likely to ask one that is attending a huge class than one who is attending a small seminar. Another interesting example is that of observed speeds while driving. Imagine a city street where the speed limit is 50 kilometers per hour, and let's ignore traffic lights and intersections for now. In this hypothetical scenario, people are on average driving at that speed, and let's say that they are normally distributed with a standard deviation of 2 kilometers per hour. In other words, if you were to stand on the side of the road and measure the velocities of passing vehicles, you would observe a distribution like this. However, unless you are a police officer, that is a very strange thing to do, and people will get suspicious that you like to do statistics for fun, and you will be an outcast. Instead, you decide to hop into the privacy of your car and collect data while driving. Since you are a good citizen, let's say you're driving at 48 kilometers per hour or slightly below the speed limit, and you start recording the velocities of the cars you encounter on the road. Sounds fun, huh? But what you see is completely unexpected. For starters, you observe that the average speed of other drivers is 51.2, and when you look at the data, the distribution of other vehicles' velocities look like this. So what's going on? Well, think about it. When you are traveling at your preferred velocity, you will almost never encounter vehicles going at your same speed. That is because you never catch up to the vehicles going at your speed, nor do they catch up to you. So in this case, you mostly observe two distinct groups of people. A small percentage of cars going slower than you, and the vast majority of cars going faster than you at 51.5. In fact, 77% of the cars you observe are going faster than the 50 kilometers per hour average, and naively, we would have expected this to be only 50%. Of course, this example can be repeated with similar results for any speeds, and the lessons would be the same. If you would be going at the average speed of 50, the distribution of car speeds you observe would instead look like this. Here, the split of different groups is very clear, which explains the experience and frustrations of driving. If you were driving in a hurry a couple of kilometers per hour above the speed limit, all of a sudden you would observe that the average cars you encounter are going much slower than the actual speed limit. To finalize, let's look at some concrete tips to avoid falling prey to the inspection paradox. Understand where the data comes from and the perspective of the data collection. Ask yourself if it was taken from inside the group or from outside. Was it out of mere convenience, or is there an incentive to prefer one over the other? Number 2, don't expect to experience the average. Remember that the average or arithmetic mean is not always reflecting the most typical experience. Number 3, make small mental adjustments and expect venues and events you attend to feel busier than what the averages imply. More often than not, you will be in crowded airplanes or restaurants, and that is just a normal experience. Cherish when you are lucky, even if it's a statistical anomaly, good luck happens, and learn to enjoy it, but not expect it. As always, stay curious, stay alert, and always look for the full picture. See you next time.